For the last decade, you've probably heard the exact same explanation every single time the jet stream goes haywire. Melting Arctic ice is breaking the jet stream. That's the line repeated in headline after headline, video after video. Except here's what almost nobody is telling you. Some of the most rigorous science ever conducted on this question has found that explanation doesn't actually hold up nearly as well as everyone assumes. It's worth pausing on just how deeply that Arctic ice explanation has embedded itself into everyday conversation. Ask almost anyone why winters feel so unpredictable lately, or why heat waves seem to linger for weeks instead of days, and you'll likely hear some version of the same answer. The melting Arctic weakened the jet stream. It's become such a reflexive explanation that it barely gets questioned anymore, repeated by well-meaning commentators, weather presenters, and social media accounts alike, almost as an established fact rather than an active area of genuine scientific dispute. The idea goes like this. The jet stream is powered by a temperature difference, specifically the contrast between the freezing Arctic and the much warmer air sitting over the mid-latitudes further south. That temperature gap is essentially the engine driving the jet stream's speed and stability. As the Arctic warms dramatically faster than the rest of the planet, a phenomenon scientists call Arctic amplification, that temperature gap should theoretically shrink. And if the engine driving the jet stream weakens, the theory predicts the jet stream itself should slow down, wobble more, and develop those large looping waves that drag Arctic cold air deep into places like the southern United States or Western Europe, while also allowing warm air to punch unusually far north in other spots. This idea first gained serious traction back in 2012, popularized through research from scientists including Jennifer Francis and Stephen Vavris, and it spread through mainstream climate reporting incredibly fast, largely because it offered such a clean, intuitive story. Melting ice up north somehow explains that brutal cold snap you just lived through down south. It's a satisfying narrative. Unfortunately, satisfying and scientifically settled are two very different things. Francis and Vavris themselves found what they described as a robust link between Arctic amplification and a slower, wavier jet stream in their original research, a finding that genuinely held up under early scrutiny and helped establish the theory as mainstream scientific consensus for the better part of a decade. Here's where the story gets genuinely interesting. In 2020, researchers Russell Blackport and James Screen from the University of Exeter published a detailed study specifically testing whether Arctic amplification was actually driving increased waviness in the jet stream. Their conclusion was blunt. They found no significant evidence that Arctic warming was making the jet stream meander more. If anything, they suggested the relationship might run backwards, with natural fluctuations in the jet stream itself occasionally influencing Arctic temperatures, rather than the other way around. That result alone would have been notable, but it wasn't isolated. In 2021, an enormous multi-year international research effort called the Polar Amplification Model Intercomparison Project delivered what many scientists consider the most comprehensive test of this theory ever conducted. Researchers ran more than a dozen separate climate models. Each simulated a full 100 times, specifically comparing atmospheric behavior with and without dramatic Arctic sea ice loss. The results were striking. Even when researchers simulated the massive sea ice loss expected by the middle of this century, the polar jet stream only weakened by tiny amounts, at most around 10% of its natural everyday swings in strength. One of the lead scientists on that project, working with the UK's Met Office, said plainly that there simply wasn't an inconsistency between continued sea ice loss and the absence of dramatic jet stream weakening. In other words, the ice keeps melting, but the doomsday jet stream collapse many assumed would follow just isn't showing up clearly in the most careful modeling available. There's an even more telling piece of evidence buried in the observational record itself. Scientists tracking jet stream behavior noticed that the especially wavy, unstable pattern observed during the early 2010s, the exact period that helped popularize the Arctic amplification theory in the first place, simply did not continue through the rest of that decade. By the early 2020s, some researchers began suggesting that the apparent trend toward a wavier jet stream may have actually been a mirage, an artifact of natural short-term variability that just happened to coincide with a stretch of dramatic Arctic warming, rather than genuine long-term cause and effect. So if it's not Arctic ice loss driving these increasingly wild jet stream patterns, what actually is? This is where the science gets genuinely fascinating, and considerably more complicated than a single clean headline can capture. Recent research has pointed toward an entirely different region of the planet as a major driver, one most people would never think to blame: the tropical Pacific Ocean. A study analyzing decades of data found that cooling sea surface temperatures over the tropical eastern Pacific have been suppressing convection along a band near the equator called the Intertropical Convergence Zone. That suppression generates what scientists describe as a Rossby wave train, a chain reaction of atmospheric disturbances that propagates directly into the jet stream's pathway, contributing significantly to the increased summertime waviness researchers have documented over the past 40 years. According to that analysis, this tropical Pacific mechanism appears to have a bigger influence on mid-latitude jet stream wobbling than Arctic amplification does, at least during the crucial summer months when heat waves tend to strike hardest. That's a genuinely significant reframing. For years, public attention has focused almost entirely on the melting Arctic as the villain behind unstable summer weather, while research increasingly suggests that sea surface temperature patterns thousands of miles away, near the equator, may be playing an equally important or even larger role. Other recent research has approached the puzzle from yet another angle entirely, examining what scientists call a fast get faster mechanism. This research found that climate change is increasing jet stream waviness in both hemispheres, but through density contrast changes in the atmosphere rather than the simple Arctic temperature gradient story most people have heard. Interestingly, this same research found that Arctic sea ice loss does still play a measurable role, specifically in a different related pattern, a slowing of mid-level atmospheric waviness in the northern hemisphere, suggesting the full picture involves multiple overlapping mechanisms rather than one single simple cause. If your head is spinning a little right now, that's actually the honest, accurate takeaway here. This is not a settled area of science with one villain and one clean answer, no matter how many viral videos and news segments present it that way. Respected researchers across multiple institutions have reached genuinely different conclusions using different modeling approaches and different sections of observational data, and the scientific community as a whole has not converged on a single unified explanation. What virtually all of these researchers do agree on, despite their disagreements over the underlying mechanism, is that jet stream behavior is changing, and that these changes are connected to extreme weather events becoming more persistent and more damaging. The IPCC's own assessment states plainly that circulation features, including storm tracks and jet streams, have shifted poleward since the 1970s, with the northern polar vortex contracting over that same period. The disagreement isn't over whether something is changing. It's over exactly which piece of an enormously complex global climate system deserves the most credit or blame for driving that change. There's yet another competing theory worth understanding here, because it adds an important layer to why scientists disagree so sharply on this question. Back in 2013, a separate group of researchers proposed something called quasi-resonant amplification, or QRA for short. Their theory suggested that a weakened jet stream becomes more prone to splitting into two distinct branches, one drifting north and one drifting south, effectively trapping weather systems in the gap between them. This mechanism, they argued, could explain why certain summer weather patterns become locked in place for weeks rather than breaking apart within days, producing exactly the kind of prolonged, damaging heat waves that have made recent summers so destructive. Follow-up research has continued examining this quasi-resonant amplification idea, with later studies attempting to identify a specific atmospheric fingerprint that reliably precedes these locked-in weather events. But just like the broader Arctic amplification debate, QRA has its own critics within the scientific community, researchers who argue the statistical evidence supporting it remains thinner than its media coverage would suggest. Other scientists examining blocking events over North America and the North Atlantic specifically have found no significant increase in their overall frequency, complicating any simple story about the jet stream becoming steadily and predictably more unstable over time. What makes this whole field so genuinely difficult to summarize in a single tidy sentence is that multiple respected research groups, using different data sets, different time periods, and different modeling techniques, keep arriving at meaningfully different conclusions. That's not evidence of bad science. It's evidence of a genuinely difficult problem, one involving an enormously complex, chaotic system with dozens of interacting variables spanning the entire globe, from polar ice sheets to equatorial ocean currents. This actually matters far beyond simple scientific curiosity, because getting the mechanism right has real consequences for forecasting. If tropical Pacific sea surface temperatures turn out to be a dominant driver of summer jet stream waviness, then predicting next year's heatwave risk requires closely monitoring ocean conditions near the equator, not just watching Arctic sea ice extent. Researchers involved in that tropical Pacific study explicitly noted that better prediction of tropical Pacific sea surface temperature variability will be essential for projecting future jet stream waviness and the extreme weather that follows from it. If you're finding this kind of nuanced, myth-busting breakdown genuinely useful, go ahead and hit that like button, because content like this only reaches more people who are tired of oversimplified explanations when you help push it forward. It takes just a second, and it genuinely shapes which videos this platform decides to show to people searching for real answers instead of recycled headlines. So where does that leave the confident, widely repeated claim that melting Arctic ice is single-handedly breaking the jet stream? The honest answer is that it's an oversimplification of a genuinely contested scientific debate, one where landmark modeling efforts have found the Arctic connection considerably weaker than popular explanations suggest, while newer research increasingly points toward the tropics, alongside broader atmospheric density changes, as equally or more important pieces of the puzzle. None of this means climate change isn't real or that it isn't influencing extreme weather. Every researcher involved in this ongoing debate, on every side of it, accepts the underlying evidence for global warming and Arctic amplification as physical phenomena. What they disagree on is the specific chain of cause and effect connecting a warming Arctic to the wavy, blocked extreme weather producing jet stream patterns showing up with increasing frequency across the northern hemisphere. That distinction matters enormously for how we talk about these events going forward. Blaming a single simple mechanism feels satisfying, but it can actually distract from the genuinely complex multi-factor reality driving today's extreme heat waves, cold snaps, and blocking patterns. Real science rarely offers one clean villain, and the jet stream's growing instability appears to be no exception, shaped by forces stretching from the melting Arctic all the way down to warming and cooling patterns in tropical oceans thousands of miles away. The next time you see a headline confidently declaring that melting Arctic ice caused this week's freak storm or record heat wave, treat it with a healthy dose of skepticism. The truth, based on the best available research right now, is considerably messier, considerably more interesting, and considerably more honest than any single-sentence explanation could ever properly capture. Understanding that complexity doesn't make the weather any less dangerous, but it does make you far better equipped to separate genuine scientific insight from an oversimplified story built purely for a viral headline. If you want more videos that cut through oversimplified viral explanations and actually dig into what the research says, subscribe to the channel so you catch every future breakdown as soon as it drops. Stay curious, stay skeptical of easy answers, and I'll see you in the next one, ready to dig into whatever headline tries to oversimplify the atmosphere next.